So what I would like to do, and otherwise we can, tailor it based on personal preference because there's only a few of you here. I just think it's really valuable to go through the review, or the reference manual that you're given during the exam, because really what else can they ask you, right? Except for what's in the reference manual. So I will do some problems and we'll talk about some things. Basically, so here's the recap of my class. It doesn't feel like it was that long ago for either of you, so, but, it's sort of fresh in my mind. And pretty much the things that we covered in Intro to Geo are a big majority of the things that I see in the reference manual, so I think those are all still valid, and the Intro to Geo space is really where you would want to focus for this. Did either of you take foundations? Yeah. So the foundation questions are pretty basic, and I don't think that not having taken the course is a disadvantage in those questions. The majority of the practice questions that I've seen and feel comfortable, sort of speculating a little bit, are really more Intro to Geo focused. So hopefully you've looked at this before, the reference manual, as you're sort of going along in your studying. I think that the geotech piece is the biggest piece within civil engineering. So if we spend a little bit of time going through this as a tool, I think that you really know what to expect for the questions that would come up in this section. So, the types of questions that we see in the practice material really are these types of questions. So let's just walk through it a little bit, and then it'll refresh your memory. And I think that's a really good use of the time in terms of refreshing what kind of things to expect there. So right off the top, it's not great, but can we handle this projection? Okay. Right off the top, the phase relationship piece, we spent a lot of time on that in Intro to Geo at the beginning, but of course, that's how we form the foundation of solving any kind of problem that's like, here's a mass, here's a volume, find void ratio, or find this, and usually they give you also a specific gravity of solids. So that's something that, we knew how to use at the time, but we might have forgotten. Something else to note as we scroll through this reference manual is that they give you the unit weight of water, and of course we use that all the time, and we knew what that was in both sets of units, pounds per cubic foot or kilonewtons per meter cubed. Then the different types of unit weights are explicitly written out for you here. So of course, I would always remind you in class that dry unit weight isn't unit weight of solids, right? And the definition of that is there. So weight of solids over total volume. And here, total unit weight on that line, they aren't explicitly putting a sub T there, but there's no other indication that it's a different kind of weight or volume, so that's going to be what you roll with. So some of these things, the notation is slightly different from what we might have seen in the Holtze-Kovacs textbook, and I think it helps to just recognize that as we go through these, but the concepts are all the same. Everything that, the water content, which we would have used in class, we first set it as mass of water over mass of solids. Of course, everything they're showing here is basically unit weights in a frame of reference, so it's going to be weights instead of masses. Here, the specific gravity of soil solids, they're giving you that definition. So it's the unit weight of solids divided by the unit weight of water. The unit weight of solids is the weight of solids over the volume of solids. So they're putting that piece in down there. That specific gravity shows up, I think, in all of the practice problems I've seen where it's the classic phase diagram problem. So it's good to remember that. Just basic definitions of void ratio, porosity, degree of saturation. Here is where they give you the sort of classically useful George Washington is a soils engineer, and I had really good feedback just a couple weeks ago from somebody that just took the exam and said, I've used George Washington as a soils engineer, so I think that it will still come in handy, and I would definitely just know that it's there, but also it's here, right, because it's so easy to remember. Relative density, by definition, in both terms of void ratio relationship and the unit weight relationships, and so those are, in either case, you're looking at comparing the maximum or minimum condition to the field condition. So in that case, they aren't putting a field subscript on this void ratio, but that's what the indication is. They do put a field subscript on the unit weight equation, so you know that you should probably be given max and min ranges and then find something field related. In class, we would have also talked about that relative compaction is not relative density. So relative compaction is a case where we have information about a Proctor test and we're trying to compare how did our compacted layer result as it compares to that Proctor test information. So the Proctor test information is the max, gamma dry unit weight max compared to the dry unit weight in the field. The top of the second column here continues that sort of basic chapter 2 material. So plasticity index, liquid limit, plastic limit, those are the Atterberg limit pieces of information. You know, the plasticity index, they're just showing you that it's just the subtraction of those two things. What I probably would expect for the use of that is then ultimately a soil classification. So I doubt that, I sort of haven't seen anything where it's like, you know, here's a grain size distribution curve, find the coefficient of uniformity. But you have those equations there if that did show up. The next piece moves into permeability or hydraulic conductivity. So we would have seen both of these. These are the permeabilities from a constant head test or a falling head test. And in these cases, I think they'd have to give you basically all of the things, you know. So a lot of this is, making sure the units come out right, you know. So even in the case where you're given some information in a problem statement and you're not even really sure what are they asking, I think a lot of it could be figured out by unit reduction. So that's just general advice. Constant head for permeability calculation, falling head for permeability calculation, they basically give you all of those things. Discharge velocity V equals Ki. Darcy's law necessarily, I don't think, shows up. Here they give you a sketch of a flow net. So the thing that, and we would have done exactly the kind of question that they would ask in this case on the exam in intro, where they aren't going to ask you to draw a flow net, but they are going to ask you probably to use a flow net, and I've seen that example in a couple different practice exams. The thing with the flow nets is that the equation that they give you is flow per unit time, and the questions that I've seen them ask are more about flow, total quantity of flow or something like that. And you just want to pay attention again to the units to know, am I multiplying by the length of the dam into the page? So that doesn't show up in this equation, but that seems to be the thing that they're asking for in these example problems. Factor of safety against seepage liquefaction. This is critical hydraulic gradient. I don't know that I've seen that in any example problem, but I think that they would just ask you something that has that piece. It has all those things that they show there in that equation. So definitely on the next page, yes. So this second page has to do with consolidation, which is something that we touched on very briefly in intro, and that might show up more in a foundations or definitely in the geotech design course. But the examples that I've seen and that we can look at, again, are somewhat straightforward. So the basics of consolidation are that you either are going to be asked to find how much settlement, so consolidation is soil settlement, how much settlement occurred, or how fast is a piece of it occurring. So this first part that you see here in the reference manual is about the how much piece, and the how much is the delta H, so change in thickness of the soil layer. And really, you know, the theory of it and going back to how things might be found, could take a long time to think about, but what they give you usually means that you could narrow down which equation to use. So we'll look at an example problem where they only give you the compression index, so compression index C sub C. That's the only piece that they give you in the problem statement. They don't give you the recompression index, which is C sub R. So if you look at these possible equations and possible combinations of comparing initial overburden pressure to the maximum pass pressure, if you're only given one of those things, it should be easy to narrow down which equation to use. So that was what I saw there. I think that probably that's the type of thing that you can expect in the question of how much change in thickness, so how much settlement is occurring for a particular compressible layer. Then we start to get into the how long piece, so how long is it going to take? Part of that is also thinking about that this consolidation is a vertical strain of that layer, so that's what they're showing you here, vertical strain, and how to calculate that based on the change in void ratio and how much the void ratio has changed, or the initial void ratio and how much the void ratio has changed in total. Of course, we're going to have some initial thickness of the soil layer, so H sub S. There is also H sub O up here, so how thick is the layer to start with. So then the time piece. So if we can find the ultimate settlement, which is that delta H, if we can find ultimate settlement and we know some way of finding the average degree of consolidation, so how much of that consolidation has occurred at a particular time, then we could find that settlement at that time. So that's what they're saying here, at some time C. So some portion of this total ultimate amount of settlement that can occur, we want to know how much of that has occurred. And that's this taking advantage of this average degree of consolidation times the ultimate amount of settlement, which is the total amount that we could expect to occur that we calculated above. I think that's all on that page. Okay. And how we do that, how we find that percentage piece, is by taking advantage of some table like this and this equation down here for the time factor. So those two pieces together would be where to look when you're faced with a question about degree of consolidation or amount of time or how much of this consolidation has occurred at this particular point in time, and the decisions to make there about whether it's one-way drainage or two-way drainage impacts this drainage distance. So the H sub dr is the drainage distance in the time factor equation. The C sub V is a coefficient of consolidation that I would think have to be given to you in a particular problem. Finding the degree or the percent consolidation can be done if you find this time factor. So this T sub V that they're giving you the equation for down below here might be something that you calculate, and then you go into this table with that T sub V, and you can find the percentage of the consolidation that's occurred. So that degree or percent consolidation, capital U is the percent of is degree of consolidation. That percentage of consolidation then would be what you are multiplying by your ultimate amount to find it at a particular time. So I have an example like that, but I think recognizing that this equation is critically important, the time factor, and then if you're being faced with a question that says how much of this ultimate amount or at this time, then you know to move towards these kinds of questions, these kinds of references. On the next page, they start to talk about, more Coulomb failure, different conditions in terms of stress, the definition of effective stress, normal stress, things that we should have remembered from, it's that. I went to sleep. Thanks. The equation for Mohr Coulomb failure is here. So shear failure equals cohesion plus normal stress times the tangent of phi. So that one I've seen in the example problems, and it's sort of hidden in this figure, but the figure is just reminding you about the Mohr Coulomb failure envelope, the use of Mohr's circle to solve these kinds of problems. So anything about normal stress, shear stress on a certain plane, this would be the place to go. Effective stress is total stress minus pore pressure. We've seen, or we'll see some example problems that have that. The thing with those is usually we have this layering of soil. We want to find the effective stress at a certain depth below the ground surface. So they do have Mohr Coulomb failure here again. I've seen where they want you to find the angle of internal friction. So shear stress equals cohesion plus normal stress times tan phi. The angle of internal friction is phi. The cohesion is c. Hopefully that rings a bell. Here, these horizontal stress profiles and forces is really the main kinds of questions that they could ask as it relates to pressure on a wall. So this is the foundations piece that I've seen, and you have some equation for active earth pressure to find this coefficient Ka. You have an equation for passive earth pressure, and the only difference is that this one is minus, this one is plus. I think they're going to tell you, so they're going to ask for what's the Rankine pressure acting on a wall. We'll see a question like that. I think they're going to say active or passive. You're not going to have to make some judgment on that. So if it's not active or passive, it's at rest, and that's those pieces here, so K naught. And that has to do with whether the soil is over-consolidated or normally consolidated. And again, I think that's something that they would have to tell you in the problem statement. So it shouldn't be that hard to know which coefficient to use in those cases. For vertical stress profiles, here these are forces, right? piece of A, active forces. These are stresses that they're showing you, so sigmas. That should give us some indication of which one to use if they ask for force versus they ask for stress. So forces, stresses, then with a surcharge. And I think that that's probably going to be beyond something that I would expect to see on these, but they include it, so at least you could recognize, okay, if they give me something with a surcharge at the surface, I could find it there. Bearing capacity is also a foundations kind of concept, but again, the thing that you might expect to find in a foundations course is a lot of tables for these coefficients, these bearing capacity factors for cohesion, depth, unit weight. They don't have the tables here, so they're going to have to give you those things. So then if you just go back to this equation for the ultimate bearing capacity, I think it's just going to be a matter of substituting in what is given in the problem statement. They give you some guidance for retaining walls in terms of factors of safety for what to check for overturning and sliding and bearing capacity. I haven't seen any example problems like that, but they have those equations there for retaining walls. Because of the way this page is oriented, also on the right upper side of this page, they talk about slope stability. So here's where we would have talked in class about, you know, we need to have some strength of the soil. So that's this T sub FF. We have to have some strength of the soil to keep it from sliding down the hill. What's making it slide down the hill? The weight of that amount of soil above the sliding plane, you know, this assumed planar slip surface. So something about slope instability, this is the place to go. Again, I don't know really how much I would expect to see the focus on that. Coming up here is two different tables for soil classification. So here we should know where we're headed when the problem is asked, you know, classify the soil. They probably will also say classify the soil according to AASHTO soil classification method or USCS classification method. So AASHTO is here. This is not one that we focused on in class. This is one where I said on the FE they include the AASHTO table, so you want to at least know that that's a different model for classifying soils. And in order to go into this table, you're making use of this equation down below, which is the group index, I think, is GI. So look for that equation. Again, I think they have to give you basically all of the things that you would plug into there. And the thing that the options that you would be coming up with, so instead of a CL for a type of clay, you would be coming up with this A4, A5, A6. Those are the answers to those kinds of questions. Here, this should look more familiar. This is the USCS table. And again, the questions here are going to be on classifying soils, but the ultimate thing that they want you to give is probably a group symbol. Here we do have some of the extra pieces where, you know, just like in class we said you have to pay attention to these superscripts and then go down to this part of the table to be able to really give the group name of a particular soil. So group symbol is sort of straightforward. Group name might have a little extra piece where you need to look down to these subscripts A through Q they have. So the last piece of that is the plasticity chart, which if you have a fine-grained soil, this is the thing to use to look into whether we have silt or clay, whether it's low plasticity or high plasticity. And those are the letters that show up there. So L for low plasticity, H for high plasticity, M for silts, C for clays, right? So that should all hopefully look somewhat familiar. Maybe. That's the table or the reference manual. So I think knowing that that's the thing, that those are the things that they could probably ask really is most of the battle, because that's what they give you, you know? So in terms of each section, not just the geotech section, but any section that you might be studying for, I don't think they're not going to ask you to come up with some wild thing. They're giving you this reference manual, and with it being a computer-based exam, I think you can control F in there. So if you, yes, no, maybe? I think so. So if you have a question, you know, that has something that you just really, I don't even know where to start, I would control F in the reference manual and just at least see what equations I have available to me, if any, in that area. So I have some example problems. This was one that I saw that I would be surprised if it showed up again somewhere else, but at least these are historically what I've seen. We could do a more classic problem before that, just so we get our feet underneath us. So these are the way they seem to form these questions. Something is most nearly blah, blah, blah. So then our choices could be so this is the classic phase diagram type problem. If you remember, you know, we have these three phases that are components of soils: solids, water, air. We would traditionally put we would put the masses on one side and the volumes on the other, and that's how they are also showing it to you in the reference manual. So you have a given 100 kilograms of wet mass. That's all the mass on the total mass on the right side. You have dry mass of 93. So you have 7 kilograms of water. We're given the total volume T of 0.0491 meters cubed. So if we want to find void ratio, if it doesn't ring any bells, I would control F in the reference manual. We should come to the equation for void ratio, which is volume of voids over volume of solids. So how do I get those component pieces? Well, I should be able to remember how to get to a volume of solids if I know the mass of solids and I know something about specific gravity, which I do in this case. So our density of solids is our mass of solids over our volume of solids. that means our volume of solids is our mass of solids over density of solids. That's specific gravity times the density of water. So with what was given, when we skimmed through the reference manual, the fact that they gave us unit weights of water makes me think that probably the problems going forward are going to be given in weights instead of in masses because it was a unit weight. But here we could come up with our volume of solids to be 93 kilograms divided by 2.65 times the density of water in kilograms per meter cubed, which is 1,000. So we could find our a number for that, for the volume of solids. The volume of voids is just this space that is total minus the volume of solids. So once we have the volume of solids number, we could find the volume of voids by our total volume minus the volume of solids, and then we have volume of voids, volume of solids, we can find void ratio. And I got 0.4 in that case. So I think my comment before was that I think that what you're going to have on this side is probably weights, because all of the things in the reference manual are given as weights. We should remember that a weight is just mass times gravity. A unit weight is just density times gravity. So we should be able to get there for those things. Okay. So this was one that I saw somewhere, mark the area of the Atterberg chart. So knowing what is the Atterberg chart would be one thing. Mark the area of the Atterberg chart provided that is associated with an elastic and elastic non-organic silt. So we might not be given the full Atterberg chart. We might have to recognize that we have to figure out where these things are. Silt is an M, so we would at least want to come to that recognition. And then there's possibilities for silt on one side versus another. What's the difference between the two? It's low or high plasticity. And we see here, with this given chart, we see elastic silts given. So, oh, now we froze.
It's frozen here.
Yeah, that seems good. So in this kind of problem, marking, I don't think we're going to see that, but anyway, it would be something like selecting that particular area. Here's another one, an undisturbed sample of soil, specific gravity of solids 2.7, moisture content 10.5, void ratio 0.63, degree of saturation is most nearly which. So here's the classic because we're given specific gravity of soils, we're given a moisture content, we're given void ratio, we can very quickly solve for saturation. And I think you're going to see one of these. Maybe it won't be as quickly evident, but maybe it will be, because I think they want to be able to ask you these kinds of questions. But this gets you through a little bit quicker. So anywhere you can save time on one question helps you with other ones that are longer, because I remember going to the review sessions for some of the structures topics, and it seemed like I'm never going to be able to answer these questions in 2 minutes or whatever you need to have as your average. Okay, so this is a question where they give you some direct shear test information, the area of the sample, the normal load at failure, the shear stress at failure, and the question is, I forgot to type it in, but the question is find the angle of internal friction. So here, basically, we might remember that for a direct shear test, we have sand, so we have a point on our more Coulomb failure envelope of 0, 0. We also have a point on that, this plot is normal stress versus shear stress. The angle that we want to find is the angle of this line, so that's our angle of internal friction. What we're given is normal load at failure and shear stress at failure. So we know that our point is going to be 16 something, but what is our normal stress at failure? And that should just, stress is just force over area, so that should bring us back to that. So the other point on our curve is 32.16. So we should be able to find that angle based on knowing that those dimensions. And I've highlighted the correct answer in these cases. So this one, the question is effective overburden stress. And in all of the example problems that I've seen, they're giving you the prompt about the units to expect. So again, I think that should start to get you to think about, what do I even need to just do to be able to get to that type of unit to answer the question? So subsurface exploration indicates that a level site has a 10-foot upper layer of sand. The groundwater table is at the ground surface. The unit weight of the sand is 135 pounds per cubic foot. The effective overburden stress is at a depth of 10 feet is what? So effective overburden stress is sigma prime. Usually we would find first total stress. And pounds per cubic feet times feet gives us pounds per square foot, so that's good. Ultimately, effective stress is total minus pore pressure, so we'd also want to find the pore pressure. We're told that the groundwater table is at the ground surface, so that's where our pore pressure starts from. We have 10 feet also of water, but we need the unit weight of water to be able to make that calculation. We're in English units, so we would use 62.4. So effective is total minus pore pressure. Our effective is 726. So anytime you're asked about, they're given a soil profile, or there are some statements about a soil profile, I think that should trigger you to, it's just a unit weight times a distance. If it's effective that they're asking for, which it has been in a lot of the example problems that I've seen, then you need to find it by total minus pore pressure. So it's not something that you're going to directly. This one about a retaining wall problem. So a 12-foot high retaining wall backfilled with granular soils with an angle of internal friction of 30 degrees and a unit weight of 125 pounds per cubic foot. The Rankine passive force per unit length. So again, they're giving you units, pound per force, possible on the wall is most nearly. So this should bring us to that section of either stresses or forces acting on a wall. They're telling you passive force. So that means I need my Rankine passive coefficient. And in that section of the reference manual, you'll also see the passive pressure. So I don't think there's anything tricky there. The KP calculation includes the feed angle. They give you the feed angle in the problem. So KP comes out to be 3. They give you that equation in the reference manual for the passive force. The unit weight they give you. So the passive pressure comes out to be 27,000. Passive force per unit length. So, I think those are going to be straightforward. The next one also is something in the foundations kind of section, but they have a strip footing, a width of the strip footing, and you would just want to go back to that equation that they give you for ultimate bearing capacity. And in this case, there's usually 3 different factors to consider. 2 of them cancel out in this case. So, did I give that to you or did I change it? Oh, the depth factor, yep. So the depth factor is 0, the n sub c is 0. I should get here. So in the absence of having those tables where you would have to make some decisions about what those factors are, and I think they have to give them to you, those bearing capacity factors, n sub c, n sub gamma, n sub q. I think that should be fairly straightforward for those types of problems too. How are we doing on time? Do we want to take a break? In that sad bag, that's where your snacks are? How are you feeling? Okay. All right. All right. Okay, so this is the consolidation kind of problem. Normally consolidated is sometimes an important piece of information, so I don't know, like you might have remembered from my class, you know, sometimes pieces of information are there written out that might be useful. So saturated, if they say something about a saturated sample, then that usually comes into play somewhere. We have a 10-foot thick clay layer with a surcharge that causes a decrease in thickness. Okay, so this is a consolidation kind of problem. The coefficient of consolidation is given, so that's the C sub D. And the time factor is given, so that's capital T sub V is given as 0.2 for a degree of consolidation of 50%. So that's where you would potentially have to use the table to get that, but here they're giving it to you in the problem statement. The clay layer is confined between two layers of dense sand. That tells me that it has double drainage if it's sand on either side. If it had bedrock on one side and sand on the other side, then I would call that single drainage. If it had more clay on the other side compared to sand on one side, more clay on the other side, that would be single drainage. In this case, sand on both sides, double drainage. The time, they want to know the time and days required for this 50% consolidation. So, like I say, they're giving you this time factor, and we saw that at the bottom of that table of values for the how long piece of consolidation. And they want to know the time in days required. So we're solving for the lowercase t. We're given the time factor as 1.2. We're in a 10-foot thick layer, but we have double drainage, which means our drainage distance is only 5 feet. And we would find the number of days that way. So that's fairly straightforward. The question here would be making use of a completed flow net to be able to answer these kinds of questions about total seepage under the dam. So this is the case where I say be careful what they are asking in a particular problem. So what we would want to do is make use of permeability times capital H times the shape factor of the drawn flow net times the length of the dam. So I point this problem out because it was offered as an example problem. If I were to think about it without being too creative in my thinking, I would have looked at, so what is this shape factor piece? N sub F is the number of flow channels, N sub D is the number of equipotential drops. So flow channels are sort of these spaces, 1, 2, 3, what I would have called 4 of those. And the number of drops 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So at first glance, I might have done 4/8 for this. The K is permeability, that's given here. So 4 times 10 to the 4 inches per second. Convert that to feet. Use the H, which is the distance between the two hydraulic heads. So the reason that they're slow under this dam is because there's a difference in water elevations from the headwater to the tailwater. That distance or difference between those water elevations is 50 feet. Our shape factor, we said, might be 4/8, and the length of the dam 600 feet. So that was my first guess at this problem. That comes out to be, I think, 4,200. If you don't use 4 as your number of flow channels, and you looked at maybe again this configuration and said that, so a properly constructed flow net, you could draw circles in between there. They should be square shaped elements. So is this one on the bottom a whole circle? So the solution had the shape factor as 3.5/8. And I point that out only because I think that's kind of nitpicky to have that as a question in that way. So, okay, so yes, if we looked at that, maybe that's half of a circle, so maybe I would have recognized that it's not 4 flow channels, it's 3.5 flow channels. So if I use 3.5/8, then I do get 3780 or 37,800. So I don't know. Would they be that nitpicky about the flow net problems? I'm not sure, but I would say at least recognize that there is a little precedent for that. So when you're looking, if you're given one of those problems and you look at it, maybe don't just say, oh, I'm going to count immediately. Look at the size of those elements to see if it really is appropriate to just go with that. So here's a type of question that we might expect as it relates to, again, finding the angle of internal friction. What are we looking for in our reference manual to be able to get to an angle of internal friction? We're looking at the Moore Coulomb failure criteria, which is that the shear stress is equal to the cohesion plus the normal stress times the tangent of the angle of internal friction. So are we given the things that we need to be able to ultimately find the angle of internal friction? Yes, we might have to just recognize that in a well-drained sand sample, the cohesion would be 0. So then we have given information about normal stress and shear stress on the failure plane. On the failure plane means we can take advantage of this equation because the sub F stands for failure. So we could solve for the angle. Normal stress, and we may explicitly say normal stress versus shear stress. Shear stress is 4,500, 6,000 for the normal stress. So we would want to solve that. arctan and come up with 36.9. Okay. It's a little small, but the stress increase due to a mat foundation at the middle of a 6-foot thick, normally consolidated layer. So the stress increase at the middle of some clay layer is, so stress increase makes me think delta P, 400 pounds per square foot. The compression index of the soil is 0.6, void ratio 1.3. If the primary consolidation settlement is 2.34 inches, the initial effective consolidation stress is most nearly. So what they're actually, the initial effective consolidation stress, what they're asking for there in the nomenclature of the reference manual is P naught. And if we go back to that section of the reference manual, the things that we are looking to use, would look something like that. This is the one where I said they only give you the compression index. They don't give you the recompression index, and so that should tell me which one of those 3 options of equations I should use. So C sub C is the compression index. That's what they give you. So I should be able to substitute in and find that. The only trick here is that the delta H, of course, is given in inches, but the initial thickness of our consolidating layer is 6 feet. That's this H naught, so we want to make sure that we get into consistent units. Compression index 0.6 log . So I had to jog my memory on how to solve the log to get this piece out, but it's possible, and maybe it's fresher in your all memories. But you know, the basic idea is this reduces down to so that's the exponent to 10 . So then you can solve for P naught. And I think, so I got 1212 in this case, and that's not too bad for most nearly in the multiple choice. So that's a use of the how much piece of consolidation. Again, I think realizing that here's what you're given, and that there are only so many possibilities within the realm of reasonableness for being asked. So here's those equations. The question, as you just saw, I think is a fair one and a good one. The stress increase at a particular consolidating layer, but they give you compression index. Not recompression index. And so compression index is that C sub C, recompression index is C sub R. If they gave you both, then okay, you have to make a decision and go back again to that handout or the reference manual to be able to say which one do I want to use, but I think they're probably going to give it more like this one. Here's another of the kind of classic phase diagram problems. So a moist soil specimen, what does that tell me? That tells me that there is probably both water and air in between those soil particles. It's not going to be fully water because they don't say that it's saturated in this problem. Moist soil specimen has a water content of 10%, void ratio of 0.6. If the weight of the soil solids, so here's where I said I think you're going to be given things as weights, not masses. If the weight of the soil solids is 2.5 kilonewtons, specific gravity of soil solids is 2.67, then what is the moist unit weight? So what we want to find, moist unit weight is a total unit weight. Total unit weight is going to be a weight over a volume, total weight over total volume. How do I get to those pieces, right? So I have my weight of solids. My total weight is over there. My total volume is over here. I have some pieces to get there. And this one actually is a few more steps of involvement because all I'm given on the weight side is the weight of the solids, but I also have a given piece of information for the water content. So we're going back and remembering that water content is the weight of water over the weight of solids, but also that the weight total is those two pieces, the weight of water plus the weight of solids. So now I have two equations, two unknowns. I can find one or either of them. Ultimately, I want to get to the total weight, right? So the weight of water is the water content times the weight of solids. Water content times the weight of solids. Weight of solids times 1 plus the water content. So I have given weight of solids, I have the water content, I can find my total weight as 2.7 kilonewtons. Then how do we take advantage of things for the other side? So I'm given a void ratio and I'm given a specific gravity of soil solids. So if I'm given a specific gravity of soil solids, I immediately should think unit weight of solids is the weight of solids over the volume of solids. I should immediately think that I have a way of getting to this piece, the volume of solids. It's going to be, we might not remember that one additional piece though. How do we take advantage of specific gravity to get to the unit weight of solids? It's just, oh, let's make sure, yeah. Thanks. Right, so that key piece, right? How do we, in the absence of being given the unit weight of solids, we always can find it by multiplying the specific gravity times the unit weight of water. In these units, then, we would want to go back and make sure that we're using the unit weight of water in units that's appropriate to us, which would be 2.67 times 9.8 kilonewtons per meter cubed. They give it to you, but it's there, sort of buried in that section of the reference manual. 2.5. So then I have volume of solids. I have void ratio. So void ratio is volume of voids over the volume of solids. So now I have the volume of voids. My total volume is the volume of voids plus the volume of solids. So then I have total volume and total weight. So I think you can expect at least one of these problems, maybe more. I think that these are kind of the things that they like to ask because, I don't know, it's the basics, right? In this case, I didn't give you the profile, but the question was, you have this soil profile given to you, 5 feet of some soil with a given unit weight, 8 feet of a second layer. They point out point O in the middle of the bottom soil layer, and they also give you that this is saturated unit weight here in this layer of 90. The water table is there. And the question is the effective vertical stress at the middle of the bottom soil layer. So this point O, what is the effective stress? And again, effective stress is total minus pore pressure. So our total stress at that depth is going to be how much weight of that top layer over what distance plus half. We're halfway through this second layer. So 4 feet of that. Pore pressure, where does the groundwater table start? What is the unit weight of water in pounds per cubic foot? So effective stress, I think that's probably what they're going to ask. And the only way to get there is by finding total and subtracting pore pressure, or remembering something about buoyant unit weight, which nobody ever does. So I think that this is the way to do it, to find effective stresses. That's basically the end of my practice problems, but I can certainly go through some other ones. How are we feeling about this section? Yeah? Anybody else? How have the other sections felt? You're more worried about one versus another, or? Well, I think there are, they get into like concrete design, right? And steel design questions. So it certainly does require, I think, a few more detailed courses than you might have done for this section. So I'll put up, they call out these particular potential questions in the geotech section. So I don't know, can I turn the light on this from somewhere? Maybe that helps a little bit. Okay. So geology, I don't know that I really think they're going to ask you a geology question. Do I think they're going to ask you an index properties and soil classification question? Absolutely. So we saw these phase relationships ones, but the soil classification problems, you might see something like this one here, where they only give you plastic limit and liquid limit, and then they say, what's the USCS classification of the soil? So all you see for options are symbols. So that should be, less worrisome than when you had to go into giving the names, because you don't have to worry about what percentage of is there a certain percentage of sand in that particular sample? And the practice ones that I've seen for soil classifications have all been fine grained soils. So they're only giving you plastic and liquid limits, and that only brings you to that silt or clay kind of decision in the USCS table. So I think it narrows it down pretty quickly. You know, once you see a problem like this, do they give you CU and CC? Do they give you the coefficient of uniformity, the coefficient of curvature? So then, okay, I have to think about, is it a gravel or a sand, and is it poorly graded or well graded? But here, if they only give you, well, first they tell you that the percentage passing the number 200 is 60%. So the dividing between the coarse grain and fine grain is whether 50% or more passes the number 200. So here, okay, we definitely have a fine grain soil, but I could have told you that because they're only giving you plastic limit and liquid limit, right? So then, is there a quick way to answer this? No, because, or narrow it down, because they are only saying C is clays and the silts for possible answers. But this low versus high plasticity piece comes by looking at the plasticity chart. So just taking advantage of those, finding the plasticity index and answering those. So soil classifications, I definitely think we'll see. Index properties, they mean things like the Atterberg limits, the coefficient of curvature, coefficient of uniformity. Phase relationships will definitely, you know, we did a couple of those example problems. I think we'll definitely see those, something like that. Lab and field tests, I don't know what they might ask there. Effective stress, we looked at 2 of those, so that's where you have a soil profile, you want to find total stress, subtract the pore pressure off of it. Active versus passive pressure on retaining walls, we did that one example. I pointed to that section of the reference manual. Again, I think they're going to have to tell you the rank, either they're going to say the Rankine active coefficient of active pressure is this, or they're going to say find the active pressure on the wall. I think they're going to tell you active versus passive. You don't have to figure that out for yourself. Shear strength, we looked at a couple examples of what I think they might ask for that, and that's, you know, given a normal stress and a shear stress, find something else. I guess they might give you a cohesion, so that would be a difference versus saying the test was done on the sand and recognizing that cohesion is 0 in that case. But the kinds of things that they're asking there are probably find the angle of internal friction, or for a given angle of internal friction, what is the shear stress at failure? So that's the kind of thing to expect. The bearing capacity, again, I think so what we see in the reference manual is ultimate bearing capacity, calculate an equation for ultimate bearing capacity. They're going to have to give you the coefficients or the coefficients to use for those calculations, and if they in the case of the one example that we looked at, that some of them are going to be 0, so that should simplify fairly quickly. I don't know what they might ask about foundation types, but I think it's more something like just that you have these available. I think it's going to be more something like one of those. A spread footing at the surface causes this increase in pressure. Use that in some way. Consolidation and differential settlement. So I don't really think anything would be asked on differential settlement, but consolidation we looked at, and that's again the how much piece or the how long piece, and that points you to a different section of the reference manual. Slope stability, they're not going to ask you about complicated things for embankments or dams. They're just going to be able to ask you about that wedge type failure and looking at that planar slip surface. It's not a circular slip surface that you would be looking at. Soil stabilization. I saw one example problem in the past that was about adding bentonite to soil to be able to use it in a landfill application, for example. And all that that problem in particular is one where I said, okay, if you can just take a breath before you answer the problem and think about what's given and what are the units that they're looking for in the answer, that's how you could come to a solution for that. And then the last two, I really don't know. I haven't seen any example problems that would point to drainage systems or erosion control. But again, there's a whole section on, I think, still maybe surveying. Is there still a section on surveying on the exam? Surveying, yeah. So we didn't take a class in surveying, but somehow we answered those questions. So I think there will be some like that, and maybe it would be those, but you know, for an expected number of questions, 9 to 14, I think we could get some good ones, just like the ones that we just did as example problems. We would get 9 of those, and those would be good questions rather than trying to make a guess on what they might ask for drainage or erosion control. So we did an example problem of each type that I would expect. We can certainly go through some others, but I feel like you're well prepared for this piece based on that. If nothing else, remember George Washington is a soils engineer. I think that's going to get you pretty far. Is that okay? Are you happy with that? All right.